Today we are jumping into a really interesting paper called General Agentic Memory via Deep Research. And it tackles what I think is one of the biggest scaling problems for AI agents right now, which is how do they handle a massive, growing history of information without just forgetting things or losing key details?
It's a huge architectural challenge.
Yeah.
And the authors, I think they correctly diagnose the root of the problem. It's this total reliance on what they call the ahead-of-time paradigm, AOT.
AOT, right.
Yeah, and if you're an ML engineer, you've felt this pain, you've run these huge offline jobs, you compress tons of context down into some lightweight memory. But compression, by its very nature, means you're losing data.
Of course. And that loss just gets worse and worse over time.
Exactly. So the solution they propose, General Agentic Memory or GAM, it doesn't just tweak this. It completely flips the script. Instead of AOT, it uses a just-in-time or JIT principle.
Okay, like a JIT compilation and programming.
Precisely. The whole computational focus shifts. You stop trying to pre-compress everything. Instead, you dynamically build the perfect context you need, but only at the moment you actually need it for a request. And they pull this off with a really clever dual-agent architecture. First, you have the memorizer. It's the more lightweight part of the system. Its job is to create a simple, structured snapshot. They call it a light memory. But, and this is the key, it also makes sure that the complete raw history is kept safe in a universal, lossless page store.
So it's keeping two sets of books in a way, the summary and the full ledger.
A perfect analogy. And then you have the heavy lister, the researcher. This is your online agent. A user asks a question, and the researcher kicks off what they call deep research. It's this iterative loop, planning, searching, reflecting, all using that light memory as a map to find the exact details in the complete high-fidelity page store.
And the results seem to speak for themselves.
Oh yeah, the performance lift is huge. GAM consistently outperforms other methods across all kinds of memory-based tasks. We're talking about significant gains over memory-free baselines like your big long LLM models, and even standard techniques like RGRAG.
Okay, let's dig into that philosophical shift first, because I love the quote they use. Intelligence is not the ability to store information, but to know where to find it. It feels like current AOT systems are all about storing, about compressing intelligence. Why does that model break down?
It breaks down because that compression is fundamentally lossy and, maybe more importantly, inflexible. Just think about the technical headaches this causes for engineers. First, and most obviously, you have information loss.
Right.
You take a 400-turn chat history and try to squish it into a summary paragraph. You're just bound to lose the little details, a specific name, a date, a number, things that might seem unimportant at the time but become crucial for a query later on.
And that pre-computed memory is all you have to work with. That leads to the second problem, right? The static structure.
Exactly. The structure is frozen. It was decided way back when the compression happened, based on what the system thought was important back then. So when a new ad hoc request comes in that needs to connect, say, a fact from session 10 with a fact from session 90 in a way no one predicted.
The system just can't do it. It stalls.
It stalls. And what do engineers do? They try to patch it with more rules and heuristics.
Which is the third limitation.
The third limitation,
Yeah.
Heuristics dependence. To make AOT work at all, you end up handcrafting all these rules, relying on domain experts. It just makes the whole system fragile. It doesn't generalize well. You can't just deploy it on a totally new task.
So the big insight from GAM and this JIT approach is, well, it's actually pretty simple. If you want truly lossless memory, the only way to get it is to have a powerful search function over the complete raw history.
That's it.
That lightweight memory, the thing the memorizer makes, it's not the source of truth anymore. It's just a map, a really good map to help the search.
It's a total pivot from a memory-centric to a search-centric view of the world. The memory just exists to make the search smarter.
Okay, so let's walk through how this dual agent system actually works in practice. You've got the memorizer doing its thing in the background, and then the researcher steps up for the hard problems.
Right. So the memorizer has two main jobs, and they happen every time a new session, let's call it a SUE, comes in. The first job is memorizing. This is the compression part. It takes the new session, looks at the existing memory, and produces concise little memo. That's your lightweight structured snapshot.
And that's the map, the index for later.
Exactly. Then comes the second job, paging, which is all about preserving the full story. The memorizer creates a special header with key context-like timestamps, what happened just before, and attaches it to the raw session data. That whole package becomes a page, which gets added to this ever-growing universal page store.
So the page store can get absolutely massive over time, but the light memory, the map, stays small and manageable.
Precisely. And that header is really important. It acts like a semantic anchor, making sure that when you retrieve a page later, you get it with all its surrounding context. The complete history is always there, fully preserved, and ready to be queried.
Okay, now for the main event, the researcher. This is the online part, where you see the full agentic power of the LLM. A user sends a request, and the researcher starts its deep research. What are the steps in that loop?
It's a really tight reflective loop. It often takes a few cycles to get the right answer. It all starts with planning. The researcher uses chain of thought reasoning, guided by that light memory, to really break down the request. It's not just, grabbing keywords. It's generating a concrete, often multi-step plan to find the information.
So it's the LLM basically asking itself, okay, to answer this properly, what specific pages do I need to go find and combine?
That's a great way to put it. And once it has that plan, it moves to the next step, searching. It executes the plan, and this is a cool detail, it can run searches in parallel, using its whole toolkit to pull the right pages from that massive page store.
And then the final and maybe most important step is the integration and reflection part.
This is what makes it deep research.
Yeah.
The researcher takes the pages it just found and integrates them with anything it found in a previous loop. Then it reflects. It asks itself essentially, do I have everything I need now? If the answer is no, it refines its request and starts the loop all over again. New plan, new search.
And if the answer is yes?
If it's yes, it packages up that perfectly assembled context and hands it off to the client agent to generate the final answer.
That search phase must need a pretty sophisticated toolkit. You said it's not just one type of search.
No, and that's critical. They gave it 3 different tools. First, the standard one, an embedding model for vector search. That's great for finding things that are conceptually similar, pages about AI safety or whatever.
Standard stuff.
Right. But then they also added a BM25 retriever for a good old-fashioned keyword-based search. And this is so important for precision. When you need to find a specific person's name or a date or a line of code, keyword search is often better.
And what's the third tool?
The third is an ID-based retriever. This one lets it do direct page exploration. So if the researcher, through its planning, figures out that the answer is almost certainly on page, say, 42, it can just go grab page 42 directly. No searching needed.
And their ablation studies showed you really need all 3, right? It's not just nice to have.
Absolutely necessary. The results in Table 3 were clear. Any 2 tools were better than one, but to get peak performance, you had to use all 3 together. It makes sense. Vector search finds the right neighborhood, but keyword search finds the exact address. You need both.
Let's talk about how they optimize this thing. It's a complex system with 2 different agents, the memorizer and the researcher. How do you train that with something like reinforcement learning?
It does sound tricky, but their approach was pretty elegant. They basically treated the memorizer and the researcher as 2 policies that need to be learned. They used standard policy gradients, and the reward signal was based directly on the quality of the final answer.
So really simple. Did the context that GAM put together lead to a good answer, yes or no?
Basically, yes. But here's the really clever part. They specifically excluded the final client agent, the LLM that actually writes the answer, from the learning loop. The optimization is purely focused on making the memory system better at its job, generating high-quality context. It means the learned policies are more general and not overfitted to one specific answer-generating model.
Smart. Okay, let's shift to the experiments. You mentioned the results were strong, and they used some pretty demanding benchmarks to prove it.
They really did. This wasn't a toy problem setup. They used Locomo, which tests conversational memory, multi-hoc, temporal stuff. They also use Hotpot QA, but, and this is wild, they tested it on context lengths up to 448,000 tokens.
Wow. 448,000, that's a lot.
It's massive, and it's designed to see how the memory system holds up under extreme stress. And finally, they used Ruler, focusing on the multi-hop tracing tasks. These are incredibly hard. They require the agent to track how a variable changes across many, many steps. It's a true test of memory and reasoning.
And you said on those really complex tasks, like Ruler, GAM didn't just do a little better, it was a night and day difference.
It was a game changer. On Ruler multi-hop tracing, GAM got over 90% accuracy. Most of the other baselines completely fell apart on that task. It also stayed incredibly stable on Hotpot QA, even as the context size exploded. It really proved that this JIT research approach scales incredibly well.
So let's break down why the other methods failed. We've got these huge 128K context windows now. Why didn't just using a big, long LLM work?
Yeah, that's such a key finding from their results. The long LLM models really suffer from what people are calling context rot. If you just dump a massive noisy history into the prompt, The model gets overwhelmed. The important facts get buried.
The needle in a haystack problem.
It's worse than that. The haystack actually makes the model dumber. The irrelevant information actively degrades the model's performance. Big context is not the same as smart context.
Okay, and what about RRAC? That's usually the fix for external knowledge. Where did it fall short?
RAG was inconsistent. It did fine on simple, single-hop questions, where the answer was stated explicitly in one place. But it really struggled on tasks like ruler that require pulling together and reasoning over information from multiple scattered sources. A standard RE system tends to retrieve isolated facts. It's not good at connecting the dots when the answer isn't obvious from a simple query.
This brings us to what might be the most interesting ablation for anyone thinking about deploying a system like this: model scale. How sensitive were the two agents, the memorizer and the researcher, to the size of the LLM powering them?
This is hugely important, yeah. The results were fascinating. The memorizer, the offline part that creates the summary, was surprisingly robust. You could shrink it way down to a tiny 500 million parameter model, and it still performed really well. And that's because its job is relatively simple information extraction.
But the researcher, I'm guessing, needs the big guns.
It needs serious horsepower. The researcher module was way more sensitive to model scale. When they swapped out a 14 billion parameter model for a 7B or smaller one, performance took a significant hit. It's pretty clear evidence that the hard part, the iterative planning, searching, reflecting, that requires a very capable reasoning engine. You can save money on the memorizer, but not on the researcher.
And finally, this whole JIT idea is built on the premise that more computation at test time is a good thing. Did the results actually bear that out?
They did, yep. Figure 2 in the paper shows it clearly. They tweaked two things. First, they increased the maximum reflection depth, basically, letting the researcher loop more times. And as they allowed it to loop up to 5 times, performance just kept climbing steadily.
More thinking equals better answers.
Pretty much. And they saw the same thing with retrieval volume. When they allowed the researcher to pull back more pages in each search, step up to 20 pages, performance also got consistently better. It's the ultimate validation of the JIT principle. Spending more compute resources at the exact moment of need directly translates to better results.
So if we pull all this together, what's the big takeaway here for someone building the next generation of AI agents?
I think the evidence is pretty compelling. The focus has to shift. We need to move away from this old AOT model of pre-computing a fixed, lossy memory. The future is enabling a smart, agentic, just-in-time search over a complete lossless history. That's how you get a truly robust and high-fidelity memory system.
And from a practical standpoint, it seems like you get this state-of-the-art performance without a crazy efficiency hit. Their analysis showed the offline build time is comparable to other methods, but the answer quality is just in another league.
It's a very effective trade-off, which brings me to a final thought for you to chew on, especially if you're architecting one of these systems. We've just established that the researcher is the expensive part, right? It's very sensitive to model scale. So what if instead of using a massive general-purpose LLM for that job, you use smaller, highly specialized models? Maybe one fine-tuned just for planning, another just for reflection. Could that be the key to unlocking the same power but at a fraction of the cost and latency in a real production environment?